The current generation of Ryobi blowers that we have designed for have a motor capable of producing speeds up to 125 miles per hour. This speed is sufficient for removing dry debris such as grass trimmings or dead leaves. However, it is not fast enough to remove heavier debris such as wet leaves or wet grass. To remove the wet debris, faster airspeed is needed. The easiest solution to instantly increase the airspeed without changing the motor is to decrease the area of the nozzle. However, constant CFM must be maintained to prevent the motor from stalling. To achieve this change in area, the simplest solution is to attach a piece to the end of the nozzle. However, this is not the best solution because attaching a piece to the blower interrupts workflow because the replacement time is too long and it's inconvenient to carry around one or more alternative tips. To address this problem, Variable Velocity Design Group will be designing an adjustable diameter nozzle attachment. The nozzle will be able to change diameter quickly and easily without having to remove it from the blower. While designing the nozzles, 7 constraints will be kept in mind. The first is that the part count has to be 6 or less. The second constraint is that the nozzle needs to be continuously adjustable. Then, with the nozzle in the closed position, the volumetric flow rate needs to be 550 CFM. Also, the air velocity needs to be 170 miles per hour in the closed position. Then the nozzle must withstand 5,000 opening and closing cycles. Also, the nozzle needs to withstand being dropped when attached to the 9.7 pound blower. And finally, the design must minimize excess noise. Each member of the VVDG came up with the design for the variable diameter nozzle. Among the designs proposed, the 2 most promising designs were the slide nozzle and pedal nozzle. When we used the CFD results as the basis of comparison, the pedal design had better airflow. The design was then further refined to comply with the constraints. Each pedal is designed with the same radial dimensions and are mounted to the blower tube attachment collar at an angle, allowing the pedals to overlap with minimal air gaps in between. The extended arm follows the shape of the blower attachment collar to be as low profile as possible, minimizing possible interference. The blower tube attachment collar matches slides onto the end of the blower tube and features an organically shaped interior surface that matches the contours of the overlapping pedals to create as smooth of an airflow as possible. There is also a lip on the inner surface that matches the inner diameter of the blower tube to create a smooth transition of airflow from blower to nozzle. The adjustment collar mounts onto the blower tube attachment collar and can be rotated to open or close the nozzle. The collar has a rigid exterior surface to help with grip and an adjustment system utilizing 8 D10 settings, allowing for the user to choose between a range of desired velocity settings and adjust on the fly. The total part count for the design is 8. This includes 6 pedals, the rotating adjustment collar, and the blower tube attachment collar. Rotating the collar forces the pedal arms up and down in the slot, which either closes or opens the nozzle. This action leads to a 19% reduction in area and a 30% increase in velocity in the fully closed position. The adjustment collar has detents that allow for the nozzle to be locked into 8 different positions. Tabs were added to the bottom of the collar to lock the adjustment collar into place, as well as make the pieces easy to assemble. The inner surface of the nozzle is stepped to match the diameter of the blower and prevent turbulence. This is how the blower with our nozzle looks. The design was validated through CFD analysis, a scale test, FEA, fatigue life estimation, and noise test. Through the CFD analysis, theoretical airspeed at steady state was estimated as 154.68 and 170.61 miles per hour for the fully open and fully closed positions, respectively. Through CFD, the region where air leaks were found. The first region is between the pedals, and the second region is at the hinges. Here's the exact amount of leakage for the extreme positions. A scale test, in which the blower was pointed at a scale to measure the air force, was conducted to compare experimental results with the theoretical results. Through the CFD, the air pressure could be estimated. The air pressure obtained from the CFD was then used as the boundary condition for the FEA to find the maximum stress. The maximum stress was 27.83 megapascals and located at the hinges. The maximum stress location matched with where the failure occurred from the stress test. To see the effects of the blower weight in case the blower was dropped on the nozzle, the weight of the blower in newtons, 43.148, of evenly distributed load was applied at the tip of the pedal. The fatigue life was estimated by using the S curve of a plastic commonly used to produce this kind of product, known as polypropylene nanocomposite. The load was assumed to be applied from 0 to 27.83 newtons repeatedly. As a result, it could withstand more than 5,000 cycles. The noise test was conducted to see if significant structural vibration caused added noise for the user when operating the blower. There was no significant structural vibration found for the variable diameter nozzle. Here is a chart of the aforementioned constraints and whether or not this design meets them. The constraints concerning air velocity, fatigue life, strength, and noise were all met. The constraints concerning part count, volumetric flow rate, and whether or not the nozzle was continuously adjustable were not all met. After discussing with the sponsor, they were satisfied with the part count and the adjustability, and felt the volumetric flow rate was secondary to the air velocity. Moving forward, this design could be improved by further optimizing the pedal design for minimal air leakage, creating a continuously adjustable mechanism, and designing a better attachment method. In conclusion, this design improves on existing solutions by increasing airspeed to 170.6 miles per hour, improving aerodynamic performance, and significantly reducing replacement time.